which will take on a day like today.
Were you able to take the exam for this class on Friday? Okay. They haven't delivered it to my mailbox yet, so.
Because there was the line question, and I remember that one. We got
Okay.
the line, so
Good.
I'm not
Okay.
hallucinating that.
It's probably still in transit right now. But if it's not there in my mailbox, but when I get back, then I'll probably grade it when I come back from Thanksgiving.
Okay, no worries. Well, you have office hours today?
Yep.
Cool. So after the break, we'll be on the other simulation software.
Yeah.
Okay.
I'm hoping we can finish all the optimization stuff today, and then we'll go in the simulation software after the break. Did not expect this computer to have MATLAB. we're in the art school, but works out. Cool.
I think you also use the body get better at like optimizing, like, cause with a little kid's body, like not know as much and not be able to optimize the task as well as someone who's older.
Oh, it's a good question, actually. So when I say optimization, it's more about load balancing, basically. And so we'll talk today about, your body's basically going to load balance to make sure that the action is as energy efficient as possible. Basically what that means is that, energy is kind of proportional to like force squared. And so, the way the body balances the loads, that every muscle that can participate in this action should contribute as equally as possible. As for little kids, I know their nervous system is kind of continuing to develop as they grow older. So they'll just have better motor control over their muscles just in general.
So maybe in that sense, but they'll be able to do it just
Yeah,
better.
maybe.
It might have a similar balance, but just not as efficient.
Exactly. Yeah. It's hard to say really. I don't know if there's been a lot of studies in terms of that actually, in terms of how efficient that is as kids grow up, because I imagine it's really hard to get data because you would need to know exactly which muscles are kind of acting at any given time. Even the stuff that we're going over, I think there's only really circumstantial evidence that the body really does this. Because yeah, there's just so many muscles in the body, it's hard to get data on every single one. But just based on kind of like caloric intake and like what they can see. Usually a lot of this stuff is measured through they basically measure the electrical impulses on the muscles themselves. Um, this is probably as close as what we can get to match like a lot of the data that we do have, but even then that data is still very circumstantial. So yeah.
I mean, I think it makes sense, just the crazy stuff that you see the body is capable of just
Mhm.
on its own, that's like, I'll buy it.
Yeah.
It sounded insane, but it's like, there's so many other things where you go like, that is ridiculously smart.
Yeah.
What it does on its own,
Yeah.
so.
The human body is fascinating. It feels like we've been studying it for hundreds and hundreds of years, but it still feels like there's so much we still don't really know about it.
Also, the grad assignment for this class is due the same day as the, report.
Yeah,
Okay,
yeah,
that's-
just at the end of the semester.
Does the final report then slash presentation, you only grade the sign information?
Yep,
Okay.
that's it. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everybody. It's Monday of Thanksgiving week, and the only reason I'm saying that is so that this is our video for any deans and provosts who have told me I'm a bum in the last few months. Here I am on Monday of Thanksgiving week teaching in the classroom. There's one other person here. Josh is here. Okay. All right. All right. So yeah, so it's Monday of Thanksgiving week. We have kind of the weird Monday, so we have a lecture today. Hoping we can finish up muscle force optimization today. And then we can move on to some simulation stuff on next Monday. Okay. So plan for today is we're going to finish up our lecture notes. I have a couple of examples to show you how muscle force optimization works. There is a companion MATLAB code that goes along with it, so we'll discuss that as well. And then we'll finish up from there. So some announcements. Obviously last time we met, there was the midterm exam last Wednesday. Haven't started grading them just yet. My plan is to grade them tomorrow. So your grade should be up before Thanksgiving. I really have no idea how people have done. I haven't even looked at them yet. So, but by tomorrow afternoon or tomorrow evening, you should know your grade. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's get back to it. So last time we were discussing here was last Monday. We were talking about muscle force optimization. Okay. So what is muscle force optimization? So, we're kind of at the tail end of our biodynamics section, right? And so far, right? So far, we've gone over two main units in this biodynamics section. So we had human motion kinematics, which was all about motion capture and the ways that we can quantify, the accelerations, angular velocities, joint angles of human motion. And we went through inverse dynamics, which took that data and converted it into net forces and net moments at the joints during a motion. Okay? So, we can summarize that by saying, so far we can take a motion and we can compute, the net forces and net moments at the joints that are needed to cause that motion. And so just to kind of remind you, let's say that we have a system that looks like this, okay? Where we have three joints here. We have, let's say this is the shoulder, we have the elbow, and the wrist, okay? Right? So far what we've been able to compute is that at every single joint, right, we have a net force and a net moment, okay? Right. Basically, what we've done is an inverse dynamics. We specify the equations of motion for every segment of the body, and we use that to compute these what we call net forces. Okay. So that's useful, of course. But usually, when we're talking biomechanics, we're interested in the actions of the individual muscles, right? And so what do we know from before? We know that whenever your body has to exert any kind of force, either to, cause a motion or to resist any kind of external forces, your muscles are the ones that are, those are the tissues in your body that are able to exert that active force, okay? The difficult thing is that in the human body, there's a lot of redundancy. And so for any given action or for any given force that's occurring at a particular joint, there can be multiple muscles that are going to participate in that motion. Right. And so for instance, for the arm here, if we just look at the upper arm, we've already discussed that, the upper arm has a muscle like this, right? And then we may have another muscle that goes like this, okay? And then a third muscle, maybe goes like that, right? So all three of these muscles can participate in a motion. In this case, we're looking at maybe like a bicep curl type of motion, okay? And now the question is, how is the body going to split the load in between those different muscles? Okay. Because if you remember from the example we did last week, because there's so much redundancy in terms of how the muscles act in the human body, right? It's possible for, one muscle to exert the entire force to produce a motion, right? That's kind of what we assumed in biostatics too. In biostatics, we only really looked at one muscle at a time. And so, that was mostly just because of the limitations of our equations of motion, okay? But, with this unit, we're introducing a new way to solve these problems called optimization. Okay. And optimization is a lot of things. But for this context, we're mostly using it to solve for systems where we have more unknowns than we do equations. Okay. And likely you've seen this situation occur in your other classes before too, because most engineering systems, at least the ones that need to have any degree of reliability, are going to have a lot of redundancy in them. And so you're going to have more unknowns or more actuators or more reaction forces than you do equations of motion, right? So like, let's say when you're designing a bridge, you don't want to design a simply supported bridge. You want to add extra supports on the bridge so that you have some redundancy, some factor of safety, to make sure that the bridge doesn't collapse under, any, once it's subjected to any kind of weird load. But whenever you add redundancy, that means you're not going to have enough equations to solve for the entire system. And so you need to kind of change the way that you solve these problems. And optimization is one way that we can do that. Okay. So that's just kind of the introduction, or just kind of a really quick recap of the introduction. I do want to pick up the example that we started last time, but before we do that, are there any questions on this stuff here? Okay. All right, so let's go ahead and pick up the example that we were working on last time. Okay, so in the example that we were discussing last time, we were looking at the ankle joint, okay? In particular, we're looking at a plantar flexion moment, or a net plantar flexion moment that's occurring at the ankle. And in particular, we're looking at a net plantar flexion moment of 100 Newton meters. Okay. All right, so just to kind of refresh your memory, we have an ankle joint, so we have a foot like this, okay? A plantar flexion moment, remember, plantar flexion is the action of when you're driving your toes into the ground. And so it's a very common action whenever you're walking or you're running. You're gonna kind of rotate, and your calf muscles are going to kind of drive your toe into the ground, usually with the intent to drive your body forward. Okay, so there's a net moment that's going this way, okay, which is 100 Newton meter. Okay. Where the ankle joint is, well, the ankle joint is a bit more complicated than that, but we can approximate it as a pin. Okay. So this dot right here is the ankle. Okay. And what we were saying was that there are 3 muscles that can participate in this action. Okay. Okay. So those 3 muscles are actually 3 different muscles that make up your calf. And so we have one muscle that maybe look like that, another muscle like that. I watched Wicked with my wife over the weekend, so I just realized these are Wicked colors, Glinda and Alphaba. And maybe another muscle that kind of acts like that. Okay. So our 3 muscles, I don't actually know if they look like that. I would need to look at a figure. But the 3 muscles that we are considering here, we have one called the gastrocnemius. 2, we have the tibialis posterior. Okay. And 3, we have the soleus. Okay. All 3 of these are muscles that are in your calf, so kind of on the back of your lower leg, right? And they look kind of something like this, right? So maybe this is your gastrocnemius muscle. Maybe the green one here is your tibialis posterior, and maybe the green one is the soleus. Okay, those are just approximations, but I just wanted to kind of draw this to kind of illustrate to you that these are 3 separate muscles. Okay. And based on the way that they're attaching to the joint here, all 3 of these muscles can participate, or all 3 of these muscles can produce a plantar flexion moment. Okay. The question is, how are they going to split that load? Okay. Okay, so that was the problem that we were working on. So basically we want to solve for the optimal value for Fg, where Fg, this is the muscle force of the gastrocnemius. Okay. We have Ft. So this is the force on the tibialis posterior. And then we have Fs, which is the force on the soleus muscle. Okay. We want to find the values for all three of these given the situations that we have here. Okay. And the way that we're going to do it is we're going to set up an optimization problem, right? We're going to set it up and then we're going to have basically MATLAB solve it for us. Okay. Because remember, the thing about optimization is that, these algorithms or these methods that we're going to use are too complex for us to solve by hand. So we just need to set up the problem and then solve it in code. Question is
the same as we did last time, because I think we finished this one.
we got up to the first objective function, but then we're gonna go over it again with the second objective function. Yeah. Okay. All right, so let's very quickly, let's go through all of the kind of the terminology, right? So that was kind of a big thing that we went over last time, was we talked about the different parts of an optimization problem, okay? First thing we are defining here is we have to define our design variables. So remember, in an optimization problem, the design variables, those are the parameters, or those are the, basically the values that we want to solve for from the optimization. And so since these three muscle forces, these are the quantity that we want to solve for. These are our design variables. Okay. And one thing you'll see very commonly, especially in these settings, is that each of your design variables has a range of appropriate values. Okay. Okay. So basically there is a lower bound for each of these muscle forces and an upper bound. Okay. So for the previous problem, I basically just gave those to you. Basically I told you each of these muscles has a maximum amount of force that they can exert. That's basically based on how many sarcomeres are in parallel in each of these muscles. But I just kind of gave it to you, right? And so I'm not going to write them down again just because it's just going to take a while, but it should be in your notes from last time. Okay. All of them also have a moment arm with respect to the ankle joint. Okay. So basically, remember, if you remember from biostatics, right? Every muscle doesn't attach directly at the joint. There's always some kind of little offset between, or little offset distance between where the muscle attaches and where the joint acts. And that moment arm combined with the muscle force tells us how much moment that muscle is going to apply. Okay. Okay. So those are the design variables. We have to identify, which variables that we're solving for. We have three in this case. We have to define their upper and lower bounds, as well as any additional information that we need for each of those muscles. So that's kind of what we did here. Okay. Next thing we need to do to set up our optimization problem is we need to set up our constraint. And so if you recall from last time, a constraint is usually a mathematical equation that must be satisfied no matter what we get from our result. Okay. And so our constraint in this case, we only have one constraint, is that together, all the muscles must produce the desired moment of 100 Newton meters. Okay. So our constraint in this case is 100 Newton meters of moment must be produced. Okay. All right, so mathematically, we're basically going to take the product of each of these muscle forces multiplied by their momentum. Okay. And so, for instance, we have 0.039 Fg plus 0.008 Ft plus 0.036 Fs is equal to 100 Newton meter. Okay. So this is one equation that has to be satisfied. So no matter what values we get from Fg, Ft, and Fs, together they have to satisfy this equation. Okay. Okay. So all that was just review from last time, right? So I'm stating it again here just because it's been a while since last Monday, but we are going to move on to something new right now. Okay. And so the last piece of information that you need to launch an optimization algorithm is you also need what's called the objective function. So the objective function is a mathematical function. So, a lot of people get them confused with the constraints a lot, okay? But the purpose of the objective function is different than that of the constraints, okay? The constraints are basically, as what the name describes, they place, they basically constrain your optimal solution in that, they have to satisfy these relationships, okay? We're lucky in this case that we only have one constraint. But you can of course expand these problems to have multiple of them. Okay. So constraints, they serve the purpose of limiting your solution, whereas objective functions, these are mathematical functions that we can use to assess, which solutions are better than others. So objective function is not really an equation that has to be satisfied. Think of them as like a rating function or like a scoring function. Okay. Okay. And so whenever you have an optimization problem, you need to have an objective function because you need to have a way to basically judge, what one solution is better, whether it's better than others. Okay. And by solution here, okay, a solution to an optimization problem is basically a defined value for all of your design variables. Okay. So for instance, if you look back in your notes from last time, we had one solution. It was fairly trivial. So this solution here, so you're going to see we're going to define values for Fg, Ft, and Fs. This satisfies the constraint, but it may not be optimal, based on other objective functions. Okay. So one example of a solution here is let's say that we have Fg is equal to 2564 newtons. Ft is equal to 0 newtons, and Fs is equal to 0 newtons. Okay. So that's an example of a solution. So when you have all three parameter values defined for a given situation, this counts as together, these three values form a solution to our optimization problem. Okay. And if you plug this back into the constraints, what you're going to see is that this satisfies the constraints. And so what we say is that this is a valid solution. Okay. So it satisfies the constraint. We have a value for all three of the design variables. So technically, it's a solution. Okay. Now, is it an optimal solution? Probably not. And so if you look at how this solution is, right? The gastrocnemius muscle is doing all the work here. So the gastrocnemius muscle is exerting 2,500 newtons of force, while the tibialis posterior and the soleus muscle, they're just chilling. They're not doing anything. Right? So this is valid, but what we could also say this is valid but not optimal. Okay. So one muscle is doing all the work, and we know that just based on kind of a lot of the evidence that we have, that this is usually not this is usually not how your body does it. And so your body's going to try to spread it out as much as possible. Okay. Okay. And so if this solution, we didn't just pull this solution out of midair. This solution was based on an objective function where we aim to minimize the total amount of force that the muscles exert in total. Okay. So this is based on okay. So our criteria for basically determining whether a solution is optimal or not is we just added up the entire, total force of the problem. Okay. So obviously, that objective function probably not ideal. And so what I wanted to do next is to show you a different objective function, right? So we're going to have basically the exact same problem. So the exact same design variables, we're going to have the same constraints. And so what I'm going to show you is that with a different objective function, it's going to change the nature of our solution, right? And so it's going to scramble up these values for FG, FT, and FS to something that is, probably more realistic. Okay. But that was kind of the last thing we went over last time, so I'm not going to kind of repeat that. So we're kind of doing like a mix of review and a mix of kind of new stuff. All right, any questions on this so far? Okay, all right. So let's look and see what a different objective function looks like. All right. So what are some other criteria that the body can use to basically balance the load between the forces, right? So we've looked at one that aims to balance the total amount of force. What about energy expenditure, or what about power expenditure? So let's try. Okay. So instead of optimizing over the total force, let's try to optimize over the total amount of power that the body has to exert to complete a motion. Okay. So energy and power is usually pretty helpful because for the most part, your body is pretty incentivized to be as energy efficient as possible. Right? We all know energy is a finite resource, and so if you can do things with less energy than rather than more energy, that's usually going to be a good thing. Okay. Okay. So how do we measure power? Right. So how are we going to measure power based on the muscle forces? Right? So from our understanding of kind of basic physics, we know that power is roughly proportional to force squared. Right? It's not exactly that relationship, but they scale somewhat similarly, right? So you take a force, you square it, that gives you a sense of how much power is needed to exert that force. Okay. So let's factor this into our objective function. Okay. So our new objective function, and so remember, usually we give the objective function the symbol little f. Okay. Little f here is going to be a function of our three muscle forces. So f of fg, ft, and fs. Okay. Let's set this equal to a function that incorporates kind of force squared. Okay. Okay. So the simplest thing that we can do is we can take each of our forces and square them and then add them all together. So we have fg squared, ft squared plus fs squared. Okay. All right, so we're basically computing a power for the amount of power that's being exerted by each of those muscles, and we're adding them all together. Okay. Okay. I'm going to do one more trick here before we finalize this objective function. So normally, when you're in optimization and you're forming your objective function, usually a good rule of thumb or a good trick to do is to make sure that every term in your objective function is unitless. Okay? Okay. For those of you in my 454 class, I think I mentioned this briefly, but when you have objective functions that are incorporating different elements or different types of quantities, you want to normalize every term just so that the units don't conflict with each other. Okay, we haven't really dealt with this all that much in the class just because of we've been doing pretty uniform objective functions, but this is a practical consideration when you're doing something like this. Okay. Now, for this objective function, all three of our terms here, they're all forces. So technically, we don't need to normalize it because they're all the same units, but it's generally a good idea to do this anyway. Okay? So for each of these quantities, right, we're still going to square them, but before we square them, I'm going to divide them by something that normalizes their value. Okay. All right, and what we're going to normalize with is we're going to take each of these forces and divide them by the maximum amount of force that muscle can exert based on its sarcomeres that we went through earlier. Okay. Okay, so we're going to divide all of these by the maximum amount of force that each of those forces can exert. Okay. Okay, and so that is our objective function. All right, any questions on this so far? Okay, good. All right, so we have everything that we need. So we have basically our design variables. They all have their upper limits. We have our constraint function that we need to remember here. And now we have our objective function that's going to let us basically assess, which solutions are better than others. Okay. All right, so what I'm going to do next is I'm going to fire up MATLAB. Okay. So I've posted 2 example scripts on Canvas. I don't think I don't think I've updated the weekly page for week 14 yet, but I will. I'll do that soon. Okay. Okay. And I was telling Josh before the class, I'm actually very surprised that this classroom has MATLAB because we're in we're in the art school. Okay. So if you go to the Canvas site, and I'll send everyone an email for this, after the class, you'll see there are 2 scripts here. So there is muscle force optimization example 1. So we're going to go through that first. And then I have the second example that we're going to go through today, which is example 2. Okay. The codes aren't very long. And so, there's no need to really stress all too much for it. A lot of this code here is just for plotting. But this is a code that you can use to optimize the muscle forces. Okay. Okay, so let's go through this code. So, I've kind of numbered each of the sections for you so that it's kind of easy to follow 1 through 7, I believe. Yep. Okay. So we come to the top here. So, first thing we need to do is we need to set the upper limits for each of the muscle forces under consideration. Okay. So for this example problem here, we have 3 muscle forces that we are, that we're going to be considering. So FG is the gastrocnemius force, FT is the tibialis posterior force, and FS is the soleus. Okay. So if you look back in your notes from last week, you'll see that these are the upper limits for all of those muscle forces. So the gastrocnemius has a maximum or an upper limit of 4,097 newtons that it can exert. The tibialis posterior has a maximum amount of 3,052 newtons that it can exert. And the soleus muscle, being kind of the big thick one, can exert a maximum amount of force of 6,435 newtons. Okay. So that's step 1. So, whenever you're doing any kind of muscle force optimization, every muscle has a maximum amount of force that it can exert, usually based on its cross-sectional area. Okay. All right, section 2. So section 2 here, we're going to define the objective function that we're going to use to minimize the metabolic power consumption. Okay. So this is exactly the function that we just went through. So we have each of the muscle forces here divided by their appropriate maximum, and we're squaring it. Okay. Now, the only interesting thing here is you would notice we're using what's called an inline function. And so we're basically defining a function here. So we're calling obj fun. Okay. Where obj fun is going to take a single argument, right? And so that argument is called f. So f here is a vector with 3 entries, where each of those entries in the f vector represent each of our design variables. So f of 1, that's going to be fg, the gastrocnemius force. F2 here is going to be FT, which is our tibialis posterior force. And then F of 3, this is our soleus muscle force, FS, that we're defining there. Okay. So, to be honest, usually I'm not a fan of inline functions just because I honestly think it's a little bit hard to follow, especially if you have a complex function. But for our case, our objective function here is fairly simple, fairly straightforward. So, I don't mind inlining it just like this, but there are other ways to do this as well. But inlining, if you have a simple function, is kind of the fastest and most convenient way to do it. Okay. So next thing that we need to do here is we're going to define our equality constraint. Okay. So remember, we have one constraint in this problem, which is to make sure that our muscles produce a maximum moment of 100 Newton meters. Okay. And so each of the muscle forces has a moment arm associated with them. So for the gastrocnemius force that had a moment arm of 3.9 centimeters, the tibialis posterior muscle had a moment arm of 0.8 centimeters, and the soleus muscle had a moment arm of 3.6 centimeters. Okay. So if you notice here, I've converted all those moment arms to meters. let me actually go ahead and comment that here. Okay. Right. And so this is the moment arm for each muscle. And the order is really important here. So you want to make sure that you kind of order your design variables in the right order every time. Okay, and then the maximum joint moment is 100 Newton meters. So we're just going to save that into a variable at this point. And then we'll save it for there. Okay. Oh, MATLAB license expires in 5 days, so we better finish this today. No MATLAB over Thanksgiving, I guess. Okay. All right, so that's section 3. So section 3, we've defined all the quantities for our constraint, and you'll see how these are combined in a second. Okay. All right, number 4. So number 4 is we need to define the initial guess for the muscle forces. Okay. So the thing is with optimization algorithms is that you have to start with some kind of initial guess. And the way that the optimization algorithm works from there is that it aims to improve that initial guess based on the objective function and making sure that it satisfies the constraints. Okay. For a problem like this, it doesn't matter. It doesn't really matter too much where you start the optimization. These objective functions are pretty well behaved. So you just need to give it dummy variables. And so you can see here that I've given an initial guess of 1 Newton for every single muscle. Okay. So you can change this too. So if you want to change the initial guess, okay, maybe all 10s, you can do that. Okay. The initial guess is just meant for the algorithm to get started. And there are situations where the initial guess matters a lot. For those of you that are in 454 are probably acutely aware of this. But for these problems, these are fairly simple on the kind of optimization problem range of how complex they can be. So we just have to start it somewhere. So we're starting at a kind of a dummy spot, which we know is obviously wrong, but the algorithm is going to improve it from there. Okay. Okay, so we can see in this section here, we've defined an initial guess for each of our muscle forces, and we've saved them all into a single vector here. Okay. Okay, section 5. Section 5 is we need to set the upper and lower bounds for each of the design variables, right? So the lower bound for all the muscle forces is 0. Okay. Just because a muscle can't exert compression, exert any kind of compressive forces. And so all of the muscle forces here have to be positive. Okay. So they all have a minimum value of 0, and their maximum value is based on their upper limits that we defined in section 1. Okay. Okay, and so you can see here, and the syntax is kind of the most important thing. So you can see here that we've saved the vectors we've saved all the lower bounds as a single vector. So our lower bounds vector is not that exciting. It's just 0, 0.0. And then for the upper bound, we have, each of the upper bounds for each of the variables. Okay. Okay. So hopefully all that is, you've done something like this before. Maybe you've never inlined a function before, but this is fairly straightforward too. Okay, so all the magic happens in section 6, right? So up to this point in sections 1 through 5, we've done everything to set up the problem. Now we actually need to go to solve it. But remember, you're not actually solving the optimization problem yourself. You're just telling the computer to do it for you. Okay. And now that we've set up the problem, the computer is able to do that. Okay. Okay. So I don't know if this is actually going to work here because there's a special optimization toolbox that you need to install. If you've done, if you're in the engineering lab, it should be installed there. Or maybe you've installed it on your computer before too, but I don't know if it's going to work here. But basically the function that you need to call is called fminCon. Okay. And so what that basically stands for is that, remember F represents our objective function. Min here means that we're going to minimize it. So we aim to minimize our objective function. The con here is meant to represent that we have a constrained optimization. Okay, so we have a constraint and we have upper and lower bounds for each of the design variables. Okay. And so you can see here that we're feeding in either all the inline functions or all the vectors that we just previously defined. Okay. So we have our obj fun, that is our objective function that we defined in section 2. We have f0 here, this is our initial guess that we defined in section 4. We have two blank vectors here. So, this F min con is actually a pretty robust function. So you can add, I believe these are for inequality constraints, these two sections here. But we don't have any inequality constraints, so we can just leave them, right? You want to make sure you include these empty vectors. And so, the function is going to be looking for these, okay? Next thing that we have here is these two things go together. So we have the moment arm vector and the joint moment. And so these are one vector and one scalar value that define our constraint. And so we define those in section 3, okay? And then finally, we're going to pass the lower bound and the upper bound, which are the two vectors that we had, defined for the lower bound and upper bound for each of the design variables, okay? Okay, and that's it. So, section 7 here is just for plotting. So, you don't have to worry about this too much. Okay. All right, so I'm going to go ahead and run this and hope that it runs. Change folder. It's fine. Assign my soul over to MATLAB. And it's running. Okay, yeah, so this is what I thought. So, this code here requires kind of an extra toolbox that's usually not installed in MATLAB by default, called the optimization toolbox. And so I don't think I can install it on here because this is a podium machine. But if you're going to run this code at home, and I recommend that you do try this. So muscle force optimization makes a great addition to your final projects. Right, it does count as one of the analysis types that we talked about before. And so if you want to add it on, there is a button from the MATLAB home screen called add-ons, okay? And I don't know if it's starting up or not. Okay, and so if you click on the add-ons button in MATLAB, it's going to open up like an app store, a MATLAB app store. Okay, okay, and you're going to search for optimization. And then there should be an optimization toolbox that you can include here. Okay. Okay, so yeah, so I don't know the sign-in credentials here. I'm not going to sign into my own account because I already have it installed on mine. But if you downloaded MATLAB from the school, you should have access to this optimization toolbox here. Okay. Okay. Any questions on how to set this up? Okay, I know that was pretty quick, but hopefully, so you'll have this recording later. And so if you do want to incorporate muscle force optimization into your final project, this is basically how you do it. Okay, so let me go ahead and bring back the MATLAB here, or excuse me, my iPad. Okay. Question is
the 7th part again? Because there was 7 and now it's the 6th.
Yeah, so the 7th one was just plotting. And so if the optimization algorithm was able to run, then that basically plotted your results and basically showed you.
Thank you.
Okay. And so, I know that was not satisfying. So let me give you the answer. Okay. So after running through MATLAB, okay. So after running this through MATLAB, we're going to have 3 solutions here. So we're going to have a value for FG, the gastrocnemius force. We're going to have a value for FT, the tibialis posterior force, and a value for FS, which is the soleus force. Okay. We have FG. Okay. What we obtained from the algorithm was that FG was equal to 820.41 newtons. Okay. FT, the tibialis posterior, was equal to 93.46 newtons. Okay. And then FS, right? So remember FS, so if you look back at the maximum muscle forces, the gastrocnemius force and the soleus force were kind of significantly bigger than the tibialis posterior force. Okay. And so you can see that's reflected here. So for the bigger muscle, you can see here the bigger muscle is being asked to shoulder, a much higher proportion of the needed muscle force, right? FG here is almost 10 times as high as FT, right? The soleus muscle was even bigger than the gastrocnemius, and so this should have a bigger share of the force as well. Okay. And in fact, our optimization algorithm was able to account for that. Okay. And so our soleus muscle here has a muscle force of about 1868.2 newtons. Okay. So this right here, this solution represents the optimal solution or optimal way for your body to break, to basically split up the load between these three muscles. Okay, good. All right, so that's a good example of optimization. So we've gone through basically the entire problem here. So we've gone through the definition of the design variables. We've gone over how to set up the constraints. We've gone over how to set up the objective function, and then as well as the MATLAB implementation. Okay. All right, so I did want to do one more example here, just because it's a little bit hard to kind of get the first time you see optimization, it's hard to grasp it. Or maybe ask people in 454, even if you see it for 12 times, it's still kind of difficult to grasp everything. So let's do another example here. This one's a little bit more complex. Okay, so with this optimization, so when you run muscle force optimization, you're not just limited to a single joint and a single batch of muscles. You can because we're using MATLAB to do the bulk of the computing. You can use muscle force optimization on much more complex systems that span multiple joints and multiple body segments. Okay. Granted, the setup is going to be a bit more complex, but compared to the computations, the setup is not that bad. Right? So let's do an optimization of the entire lower body during a running motion. Okay. So I'm not going to draw the figure just because I want to make sure that we finish this. Okay. But I am going to list out all 9 muscles that we're going to consider here. Okay. So we're going to have 9 design variables, which is pretty crazy, even by optimization standards. Okay. So we have 9 muscles. Okay. So I'm going to list out each of the 9 muscles. For each muscle that I list out, I'm going to specify the maximum amount of force that the muscle can exert, as well as its moment. So the interesting thing about the moment arms here is that, well, there's going to be multiple for some of these. So you're going to see that some of these muscles are going to cross over multiple joints, which is very common. Okay. And so some of these muscles will have multiple moment arms. And I'm going to use a sign convention to tell you whether whether this muscle is going to produce a clockwise moment or a counterclockwise moment around specific joints. Okay. Okay. Number 1. So the first muscle. So we're basically going to go from the top and we're going to go down. Okay. Well, we're going to go down the back of the leg first, and then we're going to go down the front of the leg after that. Okay. So the first muscle that we're going to consider here is the gluteus maximus. Okay. So the gluteus maximus has a maximum amount of force of 3,316 newtons. Okay. And the gluteus maximus only crosses over one joint, which is the hip joint. Okay. And across the hip joint, it has a moment arm of minus 5.6 centimeters. Okay. Yeah, there's no such thing as a negative moment arm, but I'm only using this negative convention here to let you know that it's producing a moment in the, in the clockwise direction. Okay, because we're going to have opposing muscles here too. So, for instance, we're going to be looking at the quadriceps muscles as well, or at least a couple of the quadricep muscles. And so the quadricep muscles act opposite to the gluteus maximus. And so just like this, it's going to act on the hip joint, but it's going to have a positive moment arm to indicate that it's producing a moment in the opposite direction. Okay. So again, no such thing as a negative distance, but that negative there is just for the sign convention for the moment. Okay. So the second muscle that we're going to consider is actually a group of muscles. It's going to be the hamstrings. Okay. So the hamstrings have a maximum muscle force of 3,744 newtons. Okay. The hamstrings cross over two joints. And so it's going to cross over the hip and have a moment arm of negative 5.4 centimeters. Okay. And the other moment arm that it has is that it crosses over the knee. Okay. It crosses over the knee with a moment arm of positive 4.2 centimeters. Okay. Third muscle. Third muscle here, we have the biceps femoris. Okay. Not to be confused with the biceps brachii. So this is indeed a muscle on the back of your leg. It's a little bit inferior to the hamstring. So most people think of their hamstring, which is the main muscle kind of in the back of their thigh. The biceps femoris is a slightly smaller muscle that's a little bit closer to your knee. Okay. All right. So the biceps femoris has a maximum muscle force of 1,369 newtons. Okay. And the biceps femoris only crosses over the knee joint. Okay. And so across the knee joint, it has a moment arm of 3.5 centimeters. Okay. By the way, I'm not drawing it here, but if you look into the lecture notes for muscle force optimization, there's a figure which shows you where all of these muscles actually are. Right? So I'm not drawing it just for the sake of time. I just want to get the information out to you guys, but definitely check out the figure that's in the notes. Okay. Okay. All right. So before we get down to the lower leg, let's go ahead and let's round out all the muscles in the thigh. So now we're going to the front of the thigh. Okay. Okay, so these are muscles that we often consider to be the quadricep muscles. We're not going over all the quadricep muscles here. We're going over just the ones that are important for this motion. Okay, so muscle 4 is a muscle called the iliopsoas muscle. Iliopsoas is a name that you have to say with confidence every time, otherwise you sound really silly. Okay. One of the thicker muscles on your quadricep. It has a maximum muscle force of 4,237 newtons. Okay. And it crosses over only the hip joint. Okay. But it's opposite to the gluteus maximus. And so it's going to have a positive moment arm of 4.3 centimeters. Okay. All right. Next, we have one of the other main muscles in the quadricep. This is the one that's basically kind of directly opposite to the hamstrings. So this is your rectus femoris muscle. Okay. Rectus femoris has a muscle force of 2,328 newtons. Okay. This one crosses over two joints, just like the hamstring muscle. And so it crosses over the hip with a moment arm of positive 4.9 centimeters. Okay. And the rectus femoris muscle also crosses over the knee with a moment arm of minus 4.9 centimeters. Okay. The last muscle that we're going to go over, this is another really big chunky muscle in your quadriceps. This is the vasti muscle. Okay. Sounds like a drink size at Starbucks. So this is a pretty massive muscle. So it has a maximum muscle force of 8,655 newtons. Okay. And it's basically the opposite of the biceps femoris muscle. So it only crosses over the knee. Okay. Okay. And so it crosses over the knee with a moment arm of minus 4.4 centimeters. Okay. Okay. So these 6 muscles here, again, this is not all the muscles. We're cutting the list a little bit short, just for a little bit simplicity. All of these are your upper leg muscles. So these are all muscles that are within your thigh, either the front or the back of your thigh. Okay. All right. And then from here we have the lower leg muscles as well. So some of these will be familiar. Some of these, participated in the last example as well. Okay. So number 7 here, we're going to start with the back of your lower leg. Okay, so we have the gastrocnemius. Okay. So we know this guy. We just got done with him. So we know the gastrocnemius has a maximum force of 4,097 newtons. Okay. The gastrocnemius is actually a muscle that's in your upper calf, and so it actually crosses over the knee a little bit as well. Okay. So this one actually has a moment arm with the knee. We didn't consider it before because we were just looking at the ankle, but since we're considering the entire lower body, we need to incorporate it here. Okay. So the gastrocnemius has a moment arm of 1.9 centimeters that it's going to cross over the knee. Okay. And then it also has a moment arm with the ankle that we just kind of finished discussing before. Okay. And it has a moment arm there of minus 3.9 centimeters. Okay. Remember, the gastrocnemius produces a plantar flexion moment on the ankle. Okay. And so for this diagram, and so if you look at the diagram in the notes, you'll see that plantar flexion is clockwise. And so that's why we make it a negative there. Okay. Okay. We're going to skip over the tibialis posterior. That's kind of a small wimpy muscle, so we don't need to consider it here. So we're going to skip straight to the soleus muscle. Okay. Another familiar face. The soleus muscle has a maximum of 6,435 newtons. Okay. And again, it also crosses over the ankle with a moment arm of minus 3.6 centimeters. Okay. And then the last muscle that we're going to consider in this example is on the front of your lower leg. Okay. Usually these muscles aren't that active. Dorsiflexion is not a, you don't use this to bear any loads or anything like that. But we do have a muscle on the front. We call this the tibialis anterior muscle. Okay. The tibialis anterior, it's kind of a small wimpy muscle, but it is important for dorsiflexion. So it has a maximum muscle force of 1,207 newtons. Okay. It crosses over the ankle with a moment arm of 4.5 centimeters. Okay. Okay. All right. So that was a lot. I tried to add some commentary to color it up, but It's just a raw, just large amount of numbers and large amount of names, but this is a very kind of large problem. But you know, these 9 muscles here, and I'm going to label them basically we'll label them F1 through 9 just to make it simple. But these 9 are design variables. Okay. So very quickly, you know, hopefully you can see that for a problem like this with a ton of design variables, you know, even if you had 9 equations that could solve for them, it's a very tall order to make sure that you solve for it, and all 9 muscles satisfy the constraints and satisfy their upper limits and such like that. So, you know, this is a textbook problem that, you know, you can do in MATLAB, you know, to get a result. Okay. All right. So I know I just went through the names and the stats, but any questions on this so far? Okay, good. All right. So next thing we need is the constraints. Okay. All right, so we've gone through all 9 design variables. So we have all of their upper limits, and we have all of their all of their moment arms. Okay. So our constraints in this case is going to very much kind of closely mimic the constraint that we had in our previous example. Okay. The only difference here is that we have 3 joints to consider. Okay. So starting from the top going down, we have the hip joint, we have the knee joint, and the ankle. Okay. All right, let's assume that we did an inverse dynamic study and we have the net moments that are occurring at each of these joints. Okay. Okay. So in other words, we have M hip. Okay. We have M knee, and we have M ankle. Okay. By the way, you know, you might be wondering, you know, why we're only considering moments when in inverse dynamics, if you recall, you know, we also computed the net forces at each of the joints as well, right? So that's the net X force, the net Y force. Okay. You can definitely incorporate those, and so if the net forces at the joints were non-zero, you'd basically incorporate them as a constraint, as we have here. Okay. But in order to incorporate those, you also need to know the directions of each of the muscle forces as well, which can be kind of difficult. Okay, the moments are a little bit easier to work with just because it's easier for us to quantify the moment arms. Okay. Okay. And so what we can set up here is we can set up equations based on the moment arms for each of the muscles that we have up here. Okay. Okay, so if you remember how we did it last time, basically we took the product of the muscle force multiplied by its moment arm. Okay, and the sign convention for this problem actually helped us out a little bit as well, because that tells us whether that muscle force is going to enter as a positive entry or a negative entry. Okay. Okay, for instance, and so if you look at the hip joint, right, we have 4 muscles that participate in the hip joint. We have the gluteus maximus, we have the hamstring muscle, we have the iliopsoas muscle, and the rectus femoris. Okay, so 4 muscles that can participate here. Okay, so the gluteus maximus was F1. Okay, so this right here, I'm just going to label the first one here just so that you know. So this is the gluteus maximus. Okay. So at the hip joint, the gluteus maximus had a moment arm of minus 5.6 centimeters. And so we're going to multiply this by minus 0.056. Okay. The next muscle force that is participating at the hip joint is the hamstring. So hamstrings is F2. Okay. And the hamstrings had a moment arm of minus 5.4 centimeters. Those are minus 0.054. Okay. Next, we have the iliopsoas muscle. The iliopsoas muscle is F4. We're going to add F4 to this. Iliopsoas muscle had a moment arm of 4.3 centimeters. So this is multiplied by 0.043. Okay, positive. And then the rectus femoris muscle was F5. And it had a moment arm of 4.9 centimeters. So we're going to multiply it by 0.049. Okay. Okay, so we can make similar equations for all of the other muscle forces for the other equations. Okay. So I'm just going to run through them very quickly here, but you have the numbers all in front of you as well. Okay. So for the knee joint, the first muscle that acts at the knee joint is the hamstring muscle. So hamstring muscle is F2. It acts with a moment arm of 0.042 meters. Okay. Next, we have the biceps femoris. Biceps femoris is F3. Okay. Biceps femoris had a moment arm of 3.5 centimeters. We're going to multiply this by 0.035. Okay. Next muscle that is acting at the knee joint, we have the rectus femoris, so that is F5. And it has a moment arm at the knee of minus 4.9 centimeters. Okay. Then we also have the vasti muscle, and I'm going to need the next line, so I'm just going to erase this for now. So the vasti muscle is F6. Okay. Vasti had a moment arm at the knee of minus 0.044 meters. Okay. And then we had one more muscle force acting at the knee, which is the gastrocnemius. Gastrocnemius was muscle 7, so we'll call that F7. Okay. And it had a moment arm of 1.9 centimeters. We're going to multiply that 0.019 centimeters. Okay. Okay. All right, finally, we have the ankle joint. Okay. So the ankle joint, we only had 3 muscles that could act at the ankle joint. And so the first muscle that acted at the ankle joint was the gastrocnemius, F7. Okay. So at the ankle joint, the gastrocnemius had a moment arm of, excuse me, this is negative 3.9 centimeters. So that's minus 0.039 plus. We have the soleus muscle. Soleus muscle was F8. Soleus muscle had a moment arm of minus 3.6 centimeters. Okay. And then finally, we have the tibialis anterior. Okay, so the tibialis anterior was F9, and this had a moment arm of 4.5 centimeters on the ankle. So this multiplies 0.045. Okay. Okay. So unlike the last example, where if you look at our last example, we only had one constraint because we had only one joint. Now we have 3 constraints for each of the 3 joints. Okay. Now, the reason I'm kind of spending time on this, is because we only have a precious 3 minutes left in the lecture, is that when you feed this into MATLAB, you have to kind of be careful how you feed it in. Okay. Because the way MATLAB likes this, okay. And you may have gotten a hint on it just based on our previous example code. MATLAB likes for you to feed in these constraints in matrix form. Okay. Okay. So what does that mean? So how do we go from this set of 3 equations to a matrix? Well, if you look at this, right? If you look at this equation here, you'll see that all these equations are entirely linear, right? So we have each of our design variables, F1 through F9, and they're all multiplied by just a constant coefficient, right? So whenever you have a linear set of equations like this, you can always put those in matrix form, right? So let me show you. And so if we define a vector here, so I'm going to define a vector f1 through f9, so f1, f2, f3, f4, f5, f6, f7, f8, f9. Thought I made it big enough, but I guess not. Okay. Okay. What if we multiply, specifically, what if we pre-multiply this vector key, this column vector, by a matrix? So we're going to have a matrix here just like this. Okay. So this matrix here, I often like to call it the coefficient matrix. Okay. And the coefficient matrix in this case is going to be a non-square matrix. So you kind of have to be careful about the size. Okay. The number of rows in your coefficient matrix corresponds to the number of constraints that you have. Okay. So in our particular case here for this example, we're going to have 3 rows in this matrix. Okay. And the number of columns equal the number of design variables. Okay. Which in this case is 9. Okay, so just really quickly, just because I know we're out of time, basically the way to form this matrix is that each row in the matrix is going to represent one of your constraints, okay? And what you're going to do is you're going to list out each of the coefficients in the constraint into that matrix, okay? So for instance, the first row in the matrix, you can see here that we have coefficients for F1, F2, F4, and F5, okay? So let me show you what that first row looks like, okay? So since we have a coefficient at F1, our first entry here is going to be minus 0.056. Okay. F2 is going to be minus 0.054. Okay. So those are the first 2 coefficients corresponding to F1 and F2. We don't have any coefficient on F3 for the first equation, so we're just going to leave a 0 there. Okay. Then we have coefficients of 0.043 and 0.049 for F4 and F5. Okay. And then nothing else in that equation. So F6, F7, F8, F9 are all going to be 0. So we have 0, 0, 0, 0. Okay. Okay, so that's how you set it up, right? If you want more details on this, there is, there's a little more details in the notes. I have an example code for this posted as well, so definitely check that out if you're interested in using this for your final project. This one's a much better example to look at. Okay. Any final questions on this really, really quickly? Okay, all right, so that's it for muscle force optimization. So when we come back from Thanksgiving, we're going to start talking about biomechanical simulation. And so on Monday, I have just a short lecture planned, and then next Wednesday, I have a workshop which actually shows you how to use this software. Okay, so it's exciting. I didn't get to do this the last couple of years, so you guys will be the first ones to actually use the software, which is really cool. Okay, all right, so thank you guys for coming. I hope everyone has a good Thanksgiving, eating lots of turkey. Eat lots of food, or spend time with your loved ones, family, and all that stuff. Rest up, because once we come back from Thanksgiving, it's kind of a sprint to the finish line from there. So, all right. So thank you guys for coming. Hope you have a good Thanksgiving, and I will see you after the break. Thanks, Kiera. You too.